Hi, my name is John Rice.
Hi, my name is David Outlaw.
And hi, my name is Grace Huckabee, and we are junior mechanical engineering majors at Lamar University.
And this is our project on aerodynamics, downforce, and major and minor head loss. So what is downforce? Downforce is the force pushing an object down towards the ground due to aerodynamic pressures. These are crucial in race cars as they increase traction without adding very much weight. You can generate downforce by controlling airflow around an object. This creates a pressure difference between the upper and lower surfaces of an object. As you can see in this picture, there is a Porsche 911 GT3 RS, which is known for creating thousands of pounds of downforce and has incredible track capabilities. And how exactly do lift and drag impact downforce? Lift is the opposite of downforce. Upward force created underneath the vehicle that can push the vehicle up and cause certain circumstances, just like you see in this picture here, which is a Mercedes CLR at the 24 Hours of Le Mans, taking off and flipping in the air. Drag is a byproduct of downforce, as drag is the resistance on the vehicle via the air around it.
So what is major and minor head loss in this experiment? Major head loss is due to the wall friction in the wind tunnel. Minor head loss is due to the sudden expansion in the wind tunnel. D1 is the leaf blower that is being pushed into the wind tunnel, and our D2 is the dimensions of the wind tunnel, and that is where our expansion is. Our wind tunnel is 24 inches in length, 10 inches in height. Where we are inserting leaf blower is 3 inches in diameter, and the overall width of the wind tunnel is 8.5 inches.
The car we will be using is a 1/8 scale 1969 Pontiac GTO Judge with a removable spoiler in the back.
In this experiment, we used a leaf blower that can blow 145 miles per hour and 180 miles per hour on the highest speed. We used straws to make the airflow consistent and direct it onto the top of the car. We occurred errors converting grams into foot-pounds because a full-size car does not have the same linear progression of downforce that a 1/8 scale car has. It is exponential.
Before we show the experiment, keep in mind that all of these values are negative. The higher the negative number, the more lift the car has. Our first experiment, we used no spoiler. In this experiment, we taped some straws around the leaf blower to help to produce some laminar flow. Our average was about negative 32 grams. Without the straws, the average weight was around negative 43.5 grams. Next, we do the same experiment, but we add a spoiler to the back of our car. First, we do it with the straws, and our average weight was about negative 24 grams. Next, we do the same experiment without the straws, and our weight was around negative 52 grams. Finally, we once again repeat the experiment, but this time we are using winds that are 180 miles per hour. Our first experiment shows that without the spoiler, the average weight for 180 miles per hour is negative 52.5 grams. Next, we have the same experiment, but without the laminar flow of the straws, and that's about negative 91.5 grams. As you can see in this video, the car starts to lift up since there is so much lift acting on the car. Next, we have the same experiment with a spoiler, and that weight is about negative 35 grams. And finally, we do the same experiment once again with the spoiler without the straws, and that is about negative 80 grams.
So right here, you're able to see that we have 4 constants. The first is going to be flow rate. Flow rate is going to be 0.3162 meters cubed per second. This is a constant based upon the flow rate of the leaf blower. Next, you're going to have density. Density of air is going to be 1.225 kilograms per meter cubed. Then you're going to have our diameter, which is going to be 3 inches, or converted to meters, 0.0763 meters. Finally, you're going to have viscosity of air, which is going to be 1.81 times 10 to the negative 5th pascals. We're going to start by calculating the area. The area is going to be pi times the diameter squared all over 4. In this circumstance, the area is going to be 0.004536 meters squared. Next, we're going to calculate the velocity using flow rate and area. In this circumstance, the velocity equals 69.7019 meters per second. Then we're going to calculate the Reynolds number. We're going to use the density times the velocity times the diameter all over the viscosity. The density and the viscosity, again, are the constants at the average room temperature. This is going to give us a resulting Reynolds number of 360,513.838. Now we're going to calculate the major head loss. Doing this, we're going to use the frictional factor times the length over the diameter. And the length, in this circumstance, we take 24 inches and convert it to meters, which is 0.61 meters. We're going to multiply that by the velocity squared all over 2 times the gravitational force of 9.81. This is going to give us 6.4077 as our major head loss. Now we're going to calculate the K constant for the minor head loss. Doing this, we're going to take 2 times the change in pressure over the density times the velocity squared. This is going to give us 0.45. We're going to take the 0.45 and multiply that by the velocity squared over 2 times the gravitational force of 9.81, and that is going to give us a resulting minor head loss of 111.4315. In this circumstance, we're going to calculate the force resultant of the drag coefficient by taking 1/2 times the density times velocity squared multiplied by the area times the coefficient of drag. This is going to give us 53.776. We're then going to calculate the total head loss by taking the minor head loss and adding it to the major head loss. This is going to give us a resulting total head loss of 117.8379 meters. In this experiment, we were able to calculate downforce and demonstrate how downforce is produced on a small scale via the 1/8 model car in the small wind tunnel. We were also able to demonstrate lift and drag upon a vehicle.
We were able to calculate major and minor head losses and how it's applicable in the real world and not just in theoretical applications in fluid mechanics.
We hope that you learned a lot in this video about downforces and from an engineer perspective, and we hope that you realize how crucial downforce is in the real world. Thank you for your time.